In this lecture, we are going to discuss about the collision theory for unimolecular reaction. This theory is also called as Lindemann theory. In the previous lecture, we has been discussed about the collision theory for bimolecular reactions. Actually, the collisions are takes place between the two molecules. And in bimolecular reaction, as the reacting molecules are two, then there is a collision between that two reacting molecules takes place, can be possible. But in a unimolecular reaction, only one molecule of the reactant is involved, or only one reactant is involved. So in unimolecular reaction, only one molecule of the reactant takes part in the reaction. And according to the collision theory, for the collision, at least two molecules are required. Therefore, collision theory cannot be applicable to unimolecular reaction. But the behavior of unimolecular reaction can be explained on the basis of bimolecular reactions. The behavior of unimolecular reactions can be explained on the basis of bimolecular reactions. So Lindemann suggested that the molecules acquire activation energy. He suggested that the molecules acquire activation energy through collision with other molecules. Through collision with other molecules, as a result, some molecules get activated. So in this case, the molecules are going to collide with other molecules. Collisions are takes place with other molecules. Even though the reaction is unimolecular, not only to the other molecules, but the collision between the same molecules is also takes place. So let us see here. The activated molecules decompose. Once the molecules get activated, then that activated molecules get decomposed after some time lag. After some time. And when this time lag is large, many activated molecules get deactivated. Let us take the example to explain this. Suppose A is a molecule, reacting molecule, colliding with another A molecules. The collision between these two will be takes place. So due to the collision, what happens? One of the molecules get activated. So activated molecules can be represented in this way. One of the molecule get activated and another is remains as it. Okay. So the activated molecules decomposes, means it is converted. Activated molecules decomposes to the product. After some time lag, it is converted to the product. When this time lag is large, if this process takes place in a larger time, what happens? Many activated molecules deactivated, means they are back to converted to the reactant. So time limit is there. If there is a more time takes place, then the activated molecules can be deactivated. Thus, the rate of the reaction is not proportional to the number of activated molecules, because that activated molecules get deactivated, but will be proportional to those molecules which retain activation energy. It means that that activated molecule should retain the energy. They should not be back to converted to the reactant. If they are converting back to the reactant, then the reaction takes place in the reverse order. The activated molecules should be converted into the products. They should be decomposed into the product. So in this case, the rate of the reaction is not proportional to the number of activated molecules, but will be proportional to those molecules which retain activation energy. When the rate of the deactivation is much greater, then the rate of the decomposition, the reaction will be unimolecular. The condition is given here. When the rate of the deactivation is much greater than the rate of the decomposition, the reaction will be unimolecular. Now let us consider a unimolecular reaction. How that reaction can be takes place. What is the mechanism of that reaction? So you can see here. Suppose A is the reacting molecule. A is the reactant. Unimolecular reaction. So only one reactant is there. And the conversion of A into the product. That reactant get converted to the products. Suppose that decomposition of hydrogen peroxide. So it will be takes place into water and oxygen molecule. So only one reacting molecule is converted to the product. So A is a reacting molecule and there is a formation of the product. This is one. This reaction according to the Lindemann takes place in stages. So what is the mechanism of this reaction? How we can apply the collision theory for the unimolecular reaction? In collision theory, we know that the collisions are takes place between the reacting molecules. So even though the reaction is unimolecular, the collision between the same molecules will be takes place. The A molecule get collide with A molecule. And due to the collision, the reacting molecule goes into the activated state. So A star is the molecule into the activated state. Okay. So this is 2. And once the molecule goes into the activated state, that molecules can be decomposed into the product. So the mechanism of this reaction is takes place into the 2 stages. In the first stage, one A molecules get activated giving A star and the rate constant is K1 here. You can see the rate constant, it is K1 here for this forward reaction. If there is some time lag means if this decomposition is not takes place, it takes a long time, then what happens? Then this activated molecule gets deactivated. These activated molecules get deactivated and it is back to converted to the reactant molecules. The reverse process takes place. And the rate constant for the reverse process is K2. So in this mechanism, K1 is the rate constant for the forward reaction and K2 is the rate constant for the reverse reaction. If there is a small or no time lag, then the activated molecules get decomposed. So K3 is the rate constant for this decomposition, means in the formation of the product. And the rate constant is given by K3. So K3 is the rate constant for the decomposition of the activated molecules. K1 is the rate constant for the formation of the activated molecules and K2 is the rate constant for the deactivation of the activated molecule. So the understanding of this is very important here, the mechanism of the reaction. Now let us explain what kinetic is involved in this unimolecular reaction. So first of all, let us see the rate of formation of the activated molecules. We want to find out the rate of formation of the activated molecules. So rate of formation, it will depends upon what? The rate of formation of this activated molecule, it is depends upon the concentration of this. So it is written here, the rate of the formation of the activated molecules, it is equal to K1 into A square. It is equal to K1 into A square, where K1 is the rate constant. It means we can actually write this rate of formation of activated molecules, it is directly proportional to the concentration of the reacting molecules, A square. So to remove the proportionality sign here, we have to write K1. K1 is the rate constant for the forward reaction, K1 into A square. And the reverse reaction, rate of disappearance of the activated molecules. In this reverse process, the activated molecules get deactivated, disappearance. It is back to convert the reactant. So this rate depends upon the concentration of this A star and concentration of this A. It depends upon the concentration of the A star as well as A. So you can see here the rate of disappearance of activated molecules. Reverse reaction. The rate of disappearance of activated molecules, it is equal to K2. K2 is the rate constant for the deactivation. Reverse process. It depends upon the concentration of this A star as well as concentration of A. Now, if you see the second stage, what happens there? In the second stage, the activated molecules, this A star, it is converted to the product. It is converted to the product. And what is the rate constant here? K3. So this is also the disappearance of the activated molecules. So we should have to be add that also here. Rate of disappearance of the activated molecules will be expressed in the two ways. First is that the activated molecules back to converted to the reacting molecules. Second is that the activated molecules may be converted to the product. So that is the rate of disappearance of the activated molecules. It is equal to K2 into concentration of A star into A plus K3 into concentration of A star. So we should be aware how to write this derivation. Now A star, it is a short-lived and high energy intermediate. It is a short-lived and high energy intermediate formed during the reaction. Its concentration is not known because we have not taken it. It is formed. We have taken the reactant molecules A. So A star, it is a short-lived and it is having the high energy. So concentration of A star is expressed in terms of A. Okay. So according to the steady state principle, short-lived intermediate exists in a system. Okay. There is a existence of the short-lived intermediate. The rate of the formation of the intermediate is the same as the rate of the disappearance. At equilibrium, the rate of the formation of the intermediate is same as the rate of the disappearance. Or according to the steady state approximation, the rate of the formation of the intermediate, it is same as that of the rate of the disappearance. So A star is formed in the forward step and it disappears in the backward step and also in the next step. Okay, once again I would like to write here that mechanism. The reactant A combined with collision will be expressed between these two. So due to the collision, there is a formation of the activated molecule A star and this A. So rate constant for this K1, it is K2. This is the formation of the activated molecules. And this back process, it is the disappearance of the activated molecules. And in the next stage, it is decomposes into the products. Okay. This is our mechanism of the unimolecular reaction. So K3 is the rate constant here. Now, according to the steady state approximation, actually A star, it is a short-lived intermediate. It exists for the short time. Okay, and if there is no time lag, it is immediately converted to the product. So the rate of the formation of the intermediate, it is same as that of its disappearance. Okay, so let us see here. Rate of the formation of activated molecule, it is equal to K1 into A square. It is equal to its disappearance. So what is the equation here? K2 into A star. Okay, K2, this K2 into A star into A and K3 into concentration of this A star. Okay, so we can write here K1 into A square, it is equal to K2 into A star into A plus K3 into A star. We can simplify A star is a common here. Okay, you can take this A star common. In bracket, we can write K2 this into concentration of this A plus K3. So according to this, we can find out the concentration of the A star. So concentration of the A star means activated molecule. It is equal to K1 into A square divided by this. So we are getting this. Concentration of the A star, it is equal to K1 into A square divided by K2 into A plus K3. Once again, you have to understand what is K1. K1 is the rate constant for this forward reaction. K2 is the rate constant for this reverse reaction, where activated molecules back to converted to the reactant. And K3 is the rate constant in the formation of the product, that is the activated molecules disappear here also, decomposes here also. So this is equation 4 here. So we can find out here the concentration of the intermediate or concentration of the activated complex. Now in this case, the rate of the reaction is proportional to the concentration of activated molecules. The rate of the reaction is proportional to the concentration of activated molecules. How the rate of the reaction is proportional to the concentration of the activated molecules? How it becomes? Let us say now, I would like to write here, rate of reaction is proportional to concentration of activated molecules. How it becomes? You can see here. Once again, I would like to write the reaction. Formation of this activated molecule. This is K1, K2, and these activated molecules get decomposes into the product. So the rate of the reaction can be determined according to this. Rate of the reaction, it depends upon onto the concentration of this, because product formation is important here. And rate of the reaction can be determined according to this. We cannot determine according to this because it is a reversible process, reverse process, and it is a irreversible process. So rate of the reaction is directly proportional to the concentration of this. Okay, so we can write here rate of the reaction, it is equal to rate of reaction, it is equal to, so what is the rate constant here? K3 into A star. So we'll find out this concentration of the A star. Okay, we find out the concentration of the A star. What is concentration of the A star? Activated molecules, it is equal to K1 into A square divided by K2 into A plus K3. So we can substitute here into this reaction. So rate of the reaction, it is equal to, see a rate of the reaction, it can be written in this way also. Change in concentration of the reacting molecule A with respect to time. The rate of the reaction mathematically can be written in this way. Change in the concentration of the reacting molecule with respect to time. Minus sign indicates that its concentration is goes on decreasing, means concentration of this reactant. Okay, rate of change of concentration of the reactant A with respect to time, it is also the rate of the reaction. So it is equal to K3 into A star, it is equal to this K1 into K3 into A square divided by this. So in this way we find out here rate of the reaction. What is K1 here? K1 is the rate constant for the forward reaction, K2 is the rate constant for the reverse reaction, and K3 is the rate constant for the decomposition of the activated molecules. Now in this case, this is the equation 5. So when K3 is very small, means this. If K3 is very small, means rate constant of this is very small. It means that the conversion of this A star to product is not possible. Okay, if K3 is very small in comparison to this K2 into A, means into this equation. Okay, K2 into A means this reverse process, K2 into A. Okay, so if K3 is very small, then K3 can be neglected from this equation. Okay, then the equation can be written as this equation, above equation can be written as. So we can write the equation now. Equation 5 can be written as rate of reaction, it is equal to, so it is K1 into K3 into A square, K1 into K3 into A square divided by K2 into A. If K3 is very small, then this one will be neglected. So it is K1 into K3 divided by K2 into A. But K1 is constant, K3 is constant, and K2 is also constant. So let us see how it modified. So where K is equal to K1 into K3 upon K2. This K is another constant, it is taken here. because K1 is constant, K3 is constant, divided by K2 is constant. So taking another constant here. Okay. So we get the equation there, rate of reaction. So we can write that equation now in this way. Rate of reaction, it is equal to, okay. So this is, so that can be modified as K into concentration of this. Okay. So rate of the reaction is depends upon this uh, one molecule reacting one molecule, means unimolecular reaction. When K2 into A is very small in this equation, okay, if this K2 into A is very small, means this process, reverse process, very less possibility is there. It means this activated molecules converted to the product. Reverse process is very less. Backward process is very less. So if it is very small, what happens? It can be neglected from this equation. It can be neglected from this equation. So how we can write the rate equation now? The rate of reaction, it is equal to, okay, so K2 into A is very small in that case. So that will be neglected from that equation. So it is K3. At the denominator, only K3 is remaining. Okay, so K3 get cancelled. Okay, so we can write the equation rate of the reaction. It is K1 into A square, means bimolecular. The equation 4 and 5 represent the unimolecular and bimolecular reaction. This is bimolecular now here. This is bimolecular because A square. And this is unimolecular. One A get cancelled here. This unimolecular rate of the reaction is depends upon this. But it is possible only when K2 into A is very small. Sorry, when K3 is very small. And second condition it is when K2 into A is very small. So the reaction becomes bimolecular. So we can draw some conclusion from this. The equation 4 and 5 represents unimolecular and bimolecular reaction. This is unimolecular. Unimolecular means rate of the reaction is depends upon concentration of only one reactant. And the rate of the reaction is depends upon concentration of two molecules, two A molecules. Thus, at higher concentration of A, the deactivation takes place to the larger extent and the reaction follows unimolecular reaction. So when we keep higher concentration of A, the rate of the reaction should depends upon it. Okay. And the deactivation takes place to the larger extent and the reaction follows unimolecular reaction. At the lower concentration of A, means this when K2 into A is very small comparison to the K3, the rate of the activation is almost same as the rate of the reaction and the reaction follows bimolecular reaction. So this is the kinetic involved in the unimolecular reaction. In the unimolecular reaction. So in this way, the equation 4 and 5 represents unimolecular and bimolecular reaction. And we find out the rate constant and rate of the reaction for unimolecular and bimolecular reaction. Once again, revise this topic, the Lindemann theory, collision theory for unimolecular reaction. So according to this theory, only one molecule has to be react. And according to the collision theory, for the collision, at least two molecules are required. Therefore, collision theory cannot be applicable here for the unimolecular reaction. But the behavior of the unimolecular reaction can be explained on the basis of the bimolecular reaction. We have to take the two same molecules. So Lindemann suggested that the molecules acquire activation energy through collisions with each other and molecules get activated. So you can see here the path of the reaction. Okay, the two reacting molecules A and A. So one molecules get into the activated state, that is A star, and A star is converted to the products. So this is the path of the reaction, mechanism of the reaction. And on the basis of this mechanism, we can find out the concentration of the activated complex A star. And rate of the reaction is depends upon the concentration of the activated complex. Second step. And by putting the values we derive here the derivation concentration of A star, it is equal to K1 into A square divided by K2 into A plus K3, equation 4. And that equation 4 can be placed into the derivation here, rate of reaction. It is directly proportional to the activated molecules. So we can put the concentration of A star here. So we obtain the equation 5. Thus, there are two conditions are applicable when K3 is very small in the denominator. Then K2, as compared to K2 into A, then equation can be written as, that equation can be written in this way. So rate of the reaction is directly proportional to this A. It means it is a unimolecular reaction. But if K2 into A is very small in comparison to K3, then it is a bimolecular reaction, because you can see here A square bimolecular reaction. So this is about the kinetic involved in the unimolecular reaction.